Yeah. As per the ASHRAE ethics, in this and all other ASHRAE meetings, we will act with honesty, fairness, courtesy, competence, inclusiveness, and respect for others, which exemplify our core values of excellence, commitment, integrity, collaboration, volunteerism, and diversity, and shall avoid all real or perceived conflicts of interest. As per the disclaimer, ASHRAE does not promote any brands or the product or machine appeared in this webinar for any reason. This is only for the purpose of education and knowledge enhancement among the members and non-members. Well, talking about ASHRAE, it's the American Society for Heating, Refrigerating and Air Conditioning Engineers. And it is basically the American Society to advance the heating and ventilation, air conditioning field and system designs and construction. It has more than 57,000 members all over the world in almost 132 countries. And it has members in all fields related to building construction, related to air conditioning, and various other aspects. I hope I'm audible. Somebody could just drop a message.
Yes, sir.
Yeah,
Yes.
okay, great. And theme for this ASHRAE year 2021 was ASHRAE Digital Lighthouse and Industry 4.0. And we have done lots of sessions related to this theme. I would request all of you to keep yourself muted. As a knowledge portal, ASHRAE has been very successful in taking up all the knowledge data, database, and various other aspects. It has the very strong technical committee, which includes publications, which is working on the publications, education, certification, standards, guidelines, and as per the publications till now, ASHRAE has already developed the 2019 ASHRAE Handbook HVAC on the HVAC applications. And moving on. Yes, joining ASHRAE as a now it depends on which zone do you lie. ASHRAE Chandigarh chapter has been really very active in all kinds of activities and lots of knowledge share, and so it would be really nice if you fall in this zone, in the north zone of India. You can join in the ASHRAE Chandigarh chapter. The fees and everything is mentioned online very clearly. Yeah, ASHRAE Research Promotion Committee is a very strong committee which is actively working on the research and promotion work, which manages and supports both the society level fundraising and chapter level fundraising of the research and promotion campaign. Traditionally supporting just the research work, now the RP campaign has expanded a lot, and it supports all kinds of education and endowed research through the ASHRAE Foundation. It also includes scholarship programs and lots of funds for many of the activities, technical activities being done under the ASHRAE umbrella. And you can, everything is available online also. You can very well go through the website and all the details, what kind of research funds are available, what kind of funds are they are giving out towards lots of projects are already mentioned. Like for instance, it has already funded lots of projects such as which are based on the sound and duct design, the effect of oil in the refrigerants, then the load calculations, thermal conductivity, then the simplified energy analysis procedures, weather data, refrigerant property data, fire and smoke control, and solar design. So the um, research activities are really varied, and ASHRAE is continuously supporting all the measures of the research activities. So moving on, today's webinar topic is mainly the designed on the distributed pumping, and which is basically the basically the optimized design approach towards the digitalization. And this event is sponsored by Grundfos India Limited. The speaker for today's webinar is Mr. Gaurav Mathur. He is AVP Sales and Development, Grundfos Pumps. He joined Grundfos in December 2005, and he handles the. I would just would mute yourself,
Hello.
please.
Hello.
Pramodji, if you can mute yourself, please. Yeah. Pramodji, I would request you to please mute yourself. Yeah. So, Mr. Gaurav, who is the speaker for today, has more than 20 years of industry experience covering sales, business development, and channel management. He has been involved in initialization and development of innovative products in air conditioning, pressure boosting, solar, water supply, and wastewater applications for Grundfos in India, and focuses on water and energy conservation. He is passionate about implementing digitalization in the air conditioning and water systems. Prior to joining Grundfos, Mr. Gaurav has worked with Grundfos channel partner and fully owned subsidiary of, which is a fully owned subsidiary of Prominent Germany. He has vast experiences in business development and technical sales of pumps, pumping system, water treatment equipment. Gaurav has a degree in mechanical engineering from Amravati University and a postgraduate certificate in business management from XLRI Jamshedpur. All our events are uploaded on the digital platform. The ASHRAE Chandigarh chapter also has the YouTube channel, so you can view all the sessions online as well. And this event is also being aired online, so do share the details about the event with your friends and colleagues. So let's start off with the session. Over to you, Mr. Gaurav.
Yes, thank you. Thank you very much.
I'll just give you the presenter rights.
Sure.
Yeah, just hold on. I would request all of you to kindly mute yourself. Yeah, you have the
Yeah, right.
rights.
So you can see the presentation?
Yeah.
Okay, great. So good evening, everyone. And first of all, I would like to thank ASHRAE Chandigarh Chapter for giving us this opportunity. And today what we are going to discuss is about an optimized design approach to digitalization. And we look at distributed pumping as the platform to achieve that digitalization. Now, we have divided the flow of agenda with a small introduction. Then we will look at distributed pumping and how it is revolutionizing the distribution of chilled water. We will look into the technologies which has made this possible, deep dive into the distributed pumping features and highlights, touch upon the project references where we have worked, and look into the savings calculations. And last, we will touch the technical information. So to begin with, I would like to say that this approach has been about the digital lighthouse, which just now we have seen from ASHRAE. And when we look at a system, if we do the design of a system in the correct way, we are able to achieve a certain amount of efficiency over the other systems which are possible. And once we have a better design, we make sure that we do the efficient designing of the pumps, or I have used the pumps here because it is basically a presentation more towards pumps. But what I mean to say is that based on a particular design, you go for the most efficient equipments. And you are able to achieve, by doing a better selection, a certain amount of efficiency improvement at the equipment level. You are able to achieve a certain further efficiency when you ensure that you have better maintenance and installation being done. But what actually makes the difference is when you do a better system control and commissioning. And when I say commissioning, it's an commissioning and a system efficiency control, which you do throughout the life cycle and under any load profile of your building. And that is where we say is that the holistic approach, which is a system-based approach, which gives you the platform to go to digitalization. Now, digitalization is a big word, and I would like to summarize digitalization. It's about change in culture. It is a change in the mindset, the way we look at our systems and buildings. And this is a mindset change when we go from a thumb rule based design to a detailed analysis design. And we do a strong planning and strong system design right in the beginning. It is a change from a data recording to actionable insights. And it is a mindset from looking at the equipment efficiency only to a continuous system efficiency improvement. And that is what we say as an overall digitalization. Distributed pumping is a part or is a way in which you can achieve digitalization. And distributed pumping is a paradigm shift which builds a strong platform for digitalization. And we will see during this presentation how do we actually achieve that. Now, currently, if we see, it is a picture which actually shows what is currently happening in terms of the design which are possible today. So I have made that today's design in a very small picture, but it has various different forms available in the form of a primary, secondary chilled water pumping system, a variable primary chilled water pumping system. For the purpose of our discussion, I have taken a variable primary chilled water design where you have a set of pumps which are pumping the water through the chiller evaporator coil, and the chiller from those pumps are pumped to the entire circuit. I have simplified the design just for the ease of understanding, but Of course, there are many complex dimensions to it. But for the ease of understanding, what we are essentially seeing is that there is a pump which is pressurizing the entire circuit. And the takeaway from this slide is only that you have a set of pump, or you have pumps in the plant room which are actually pressurizing the entire circuit. And for the flow control for individual AHUs or FCUs, what we are using is the throttling mechanism. It can be with the help of manual or automatic balancing. That there are various ways you do that. But essentially, what you're doing is you are generating pressure and then killing it. What we see in a distributed pumping system is that we have pumps, as you can see, being connected to individual AHUs. And we have a pump which caters to the production loop, or which caters to the chilled water production, which is separate from the pumps which are there on the secondary side. So this is one of the change which happens. And this is the only difference I would like you to look at for this part of the presentation, and we will deep dive and see what are the other features which are there and how the difference happened. But essentially what we are doing is that instead of killing the pressure which a single set of pumps which creates in the production area by the way of throttling, we are essentially moving it in the form of pumps and ensuring that we do the pressure requirement as it is needed. And what it gives us, these are the three key takeaways which will revolve around my entire presentation. Is first is easy commissioning. The second is minimum pressure, maximum savings. And the last but not the least is the demand driven system. These are the broad three takeaways from this presentation. Now, before we go deeper into the design part of it, we look at each of these benefits and how do we actually achieve them. When I say easy commissioning, what does that mean? Is that you do not have to spend a lot of man-hours to do the commissioning. You have to make sure that the pumps adapts itself to the requirement at any load conditions. So these are two things we are looking at. One is from the initial point of view, you need lesser manpower and lesser number of man hours to ensure that the commissioning happens. And then you need a system which adapts itself to the different load conditions. And how this is possible? Because you now have the pumps for their exact need. I will go briefly into it. What I mean by we have the right pump for the right uh, uh, so what do we mean by the right pump for the right pumping need? Is that the pump which is there in the production loop is designed for the loop in the production side. So with the help of these arrows, you can understand that the pump in the production loop or the primary chilled water pump size has reduced drastically. So this is what I mean, that right pump for the right pumping needs. And this is the one change which you see, is that there is a reduction in the size of the primary chilled water pump depending upon your production loop friction losses. So this is the loop based on which your primary pump is designed. And the first pump on the secondary side, which is nearest to the plant room, is designed based on its individual loop. So what is the loop for which this pump is designed? Right from the decoupler to the pump and back to the decoupler. So this is how you have the right pump for the exact requirement it is meeting. Similarly, as we move further away from the plant room, the design of that particular pump happens based on the friction loss in this particular loop, and so on and so forth. So this is how, as you move further away from the plant room, you have the pump which is designed as per its exact requirement. And that is what actually makes the whole system self-balancing, because here you do not have uh, um, any kind of restriction or any kind of uh, a pressure uh, difference which is happening for the particular loop for which a pump is designed. And we will go deeper into it. Sorry. Okay. Okay. 1 minute. Oh. Is it visible now? Okay. Thank you. Thank you very much. Thank you.
Okay.
So, so this is what is happening when you are designing the pump as per the exact requirement. The second point, which we have seen as one of the key benefits from distributed pumping, is a minimum pressure solution. That means a decreased flow and pumping energy usage. So you have seen the size of the primary pump has reduced because the head for which the primary pump is designed is much lesser as compared to the conventional system, because now it is designed only for the friction loss in the plant room. This is one of the picture which actually depicts that how the size of the pump, which has reduced from a much bigger pump to a much smaller pump. The third point is a demand-driven solution, and it is very important when we look at a system where you ensure that the system is meeting the requirement of the chilled water as the load changes. So if you look at this pump, which is connected with this particular AHU, this is being controlled based on the temperature sensor from this AHU. This pump is controlled based on the temperature sensor from this AHU, and so on and so forth. So there is a localized control. The entire intelligence is in the pump at that particular location, and that is what we mean by demand-driven solution. How the control happens, we will touch upon later, but this just gives you the benefit that at any load condition, the pump is going to vary its speed to make sure that it is meeting that requirement. And that goes for all the pumps on the secondary side and also the pump on the primary side. Now you will ask a question that I have said that the pumps on the secondary side can get a control based on the temperature sensor from the AHU. But how does this primary pump get controls? So we will go into deeper on the controls for the primary pump. But for the purpose of this time in the presentation, these pumps are controlled by the localized temperature sensor across the decoupler. So what you see essentially here is that all the pumps are distributed in the circuit and they all have a localized control. So you do not have a remote sensor which is controlling a pump at a distance, and all the pumps are controlled by temperature. And that is exactly what is the most important thing when we do demand-driven solution. You do not have an indirect way of controlling the pump. What is the indirect way? When you have a temperature signal going to a flow restricting device like a flow modulating valve, and when the valve closes, it is a pressure reading which the pump actually takes and based on which it modulates. That is a way in which we do a, a control which is indirect. But here you have a direct temperature based control happening for the pump. And that is what makes it a demand driven system and automatic load balancing of each of the branch at any load condition. Now let us go deeper into it and see one of the examples where we have implemented this particular distributed pumping project in Singapore. This is Nean Polytechnic. It's an educational institute. It is a gold-rated green building. It's a platinum-rated green building already by the time when we reached and did the audit there. And after the audit, when we implemented the distributed pumping system there, where we installed around 15 Magna pumps. This is the circulator pump. And we changed the primary pumps, and you can see the size of the pump has reduced from 5.5 kilowatt motor size to 1.5 kilowatt pumps. This is the amount of savings we achieved from the baseline. And we have been able to achieve more than 50% saving on the pumping cost. We also had seen an improvement in the delta T of the overall system because it's a temperature-based control. But this is something which can vary from site to site. So we do not really say that these are the kind of savings we can attribute to any site. But this is a very important point for us to mention, that when you have a temperature-based control in the system, it does improve the efficiency of the chiller. And that is where you can see how the connect is happening when you have a approach which is only on the equipment based and compared to an approach which is a system based. But how this change is possible? We already have a system which is a conventional system, and we already have been able to achieve a lot of savings, and we have been supplying a lot of pumps with a variable primary design and with a primary secondary design, and still it is one of the major ways in which chilled water is distributed in the market today. But then what has changed for us to bring this new concept in the market? And distributed pumping is also not something which we have brought in. It has been there for many years. It has been used, that concept has been used in district cooling application, where your building pumps were designed for their individual loops rather than only for the building which they are giving. So it is not that something distributed pumping is a concept which we have brought in. But what has made this possible is the change in the technology which has happened. And we have been able to achieve the the pumping systems which are highly efficient. So when I go for a distributed pumping system, we have to make sure that the pumps are designed for the highest possible efficiency to ensure that we are able to achieve operational savings which can make the system commercially viable. So that was the first thing which we say is what we achieved out of it. The second is that the entire intelligence is there in the pumps. So as you can see on your screen, the Magna 3 and the TBE3 pumps of Grundfos have a built-in intelligence and controllers. It has built-in sensors which ensures that the system performance, or the performance which is localized to that particular equipment, is optimized at any point of time. And this is made possible with the help of the pumps hydraulics which we have changed, plus the advancement which has happened in the kind of motors which we are using. So it is the change in the technology which has made this possible. Another thing which is important is that, and which is again a, a, a very strong point for us to look at distributed pumping as a strong platform for digitalization. There is a communication network which is possible under different protocols, whether it is BACnet, Modbus, and the entire data from the pump can be taken to a management system. And the host of data can be recorded, and we can then generate patterns for optimization. Actionable insights can be done by digging the data. We can ensure that with the help of communication which is possible, we are able to adapt these pumps based on the changing outdoor conditions. So the most important thing is that if I would like you to visualize for a moment that when you design a building, you have the total load of the building available with you. How about if you know what is the load in different areas at different timings, and how much chilled water is going into different area, and to the level of knowing what is the flow going into an individual AHU. That level of data can give you a lot of information which can convert into actionable insights. And all this is available at the real time. So the control of these pumps can be done based on the changing outdoor conditions and based on the optimization algorithms which can run to ensure that the system performance is optimized at any point of time under any load conditions. I will touch upon the few features which has made this possible, and one of the things is a feature is known as flow limit, where, as I said, the pumps which we are talking about, Magna 3 and TPE3, are able to measure the flow. And as you have the flow reading available, it can make sure that a limit can be set on the flow. And that is where we say that it acts as a balancing function also, because here you can limit the flow and ensure that for a particular equipment, the flow never increases beyond a point. Which you can see with the help of this picture that you can eliminate the balancing part of it by using this function. And that is why we say that the pumps are no longer pumps. You have no longer just pumps. They have the pump features to the most highest efficiency point. With the flow limit kind of functions, we have the pump throttling function possible, because now you are actually limiting the flow. We also have a feature where you can measure the heat energy estimation for a particular zone in case of zone pumping. And since the entire controller is inbuilt, you have an inbuilt commissioning assistant. So what I say is that the pumps are no longer pumps, and they have a lot of intelligence inbuilt, which makes sure that we are able to achieve the efficiencies we are looking at in a distributed pumping. And that is the reason this has become commercially viable. So the question which can come to your mind is, why, if distributed pumping concept has been there for so many years, why it has not been a commercially viable solution? So the answer is the technologies have changed, and now we are able to achieve the kind of efficiencies we are looking at, the kind of controls we are looking at, and that is how the system becomes viable. And we will touch upon during the savings part that how much are the kind of savings we can see. Uh, as I already mentioned, that we have IE5 efficiency motor, which is a permanent magnet motor, where you are able to see a further efficiency improvement of about 5 to 7% overall, as compared to the other efficiency class currently available in the market. So this is the highest efficiency motor which is possible with the help of our Magna 3 and TPE3 pumps. One more feature which actually makes the system much more reliable, and just a few days back we had a panel discussion, and where one of the points was discussed that why do we really need standby pumps? If the pumps are reliable enough to ensure that they are giving a trouble-free life, then why do we really need standby pumps? And that is an answer from Grundfos to this requirement of the market, that we have a Magna 3 pump, which is a mechanical seal-less pump. And if you see any data from any pump manufacturer you take, the maximum failure in a pump happens at the area of mechanical seal. And this pump is actually a sealless pump and ensure that the reliability factor and maintenance-free operation is achieved with the help of Magna 3. So these are a few features which I thought will be important. It's a small video. It will give an idea
The
on the
Magna
commissioning.
3 is our state-of-the-art large circulator, and it's the pump you'll want to bring when your big customers ask for heating or cooling with world-class efficiency. Once you've got the Magna 3 firmly in place, start by simply loosening the new clamp ring screw so you can turn the pump head. The pump head must always be fixed in the 3 o'clock position, since the Magna 3 is air-cooled. If the pump needs to be connected to a control and monitoring system, all you need to do is put in the appropriate CIM module. This is easily done, and a huge improvement on the time when you had to mount a separate CIU box on the wall next to the pump. Another improvement from an installer's perspective is that the Magna 3 communicates via wireless radio. This means that you can now simply slide a dongle into your smartphone and set up the Magna 3 through the free Grundfos Go remote app. With the built-in startup guide, this will be quicker, easier, and a lot more comfortable than it used to be. And once you're done, you can even generate a report and send it to your customer on the spot. Job done. That's how you make your big customers happy, without even breaking a sweat.
So that was a small video just to showcase how easy the commissioning is. And on your screen, what you see is actually the screen of a Magna pump, and you can see the amount of data which is available here and how easy it is to do the commissioning, because you do not need to go one screen behind the other, or you don't need a manual handy to do commissioning. Everything is on the screen and it is visible and it is driven by the commissioning assistant. So it makes the entire commissioning much more easier. We also have pumps available in a twin head mechanism, and where you need not have a common header to be made for twin pump operation. We have an inbuilt casing which has an inbuilt NRV and a common header to ensure that you have a twin pump operation available. Now let us go a bit deeper into seeing that we can talk about so much of savings in pumps, but there has to be some the logical answer that how those savings actually happen. And and that is what we see here is, if you see a conventional system, you have something called as a system curve, and that is where you see that the system curve is changing with the changing load requirement. And this is essentially is what is happening when you have a load variation happening in case of a conventional system. So what is happening is you have the walls closing and you have the system curve moving towards the left. So I'm sure you all are aware that when a throttling happens, what happens to the system curve. And based on this changing system curve, we are able to achieve the savings by moving the set point to make sure that we achieve the flow requirement in the most optimum way. But as you can see, the way this white curve is moving, you have a conventional system where the pressure keeps on increasing with the help when you have a load happening. Whereas if you look at the system curve in case of a distributed pumping system, it is not moving because there is no throttling happening when you have a distributed pumping system. And if you see this green dotted line as well as this red dotted line, the gap between this is the energy saving advantage which you have with distributed pumping. Now, what do you observe here? As the load is very close to the full load condition, you have lesser difference. But when the load goes down, when the flow requirements are less, that is where you have the maximum savings, even in some cases more than 50% happening. And that is a simple system curve way of looking at it. And this is where the change, the energy saving is coming from. This is one of the areas where the savings are coming from. The other areas where you look at the saving coming from is when we will touch upon the savings aspect, both in terms of CapEx and in terms of OpEx. But let's look at the controls part, which we discussed right in the beginning, that you have a temperature-based control for the pump which is connected with the AHU. So this is basically a air temperature sensor. You can connect it with the pump and you can put the set point in the pump for the temperature requirement. You can have a supply air temperature or a return air temperature. These are our recommendation that if you have a variable volume, you should go for a supply air temperature. If you have a constant volume, you should go for a return air. But then it is as per your design, you can let us know. Either ways, we can put the set point in the pump and run the pump as per the requirement. We also have a NRV, because here on the secondary side, you have the pumps connected in parallel. So you need to ensure that there is no backflow of water coming in. So an NRV is required along with each pump in the circuit. And the controls for the primary pump, we will touch base a little bit in a while. But if you look at the coil characteristics, and I'm sure you all are aware that you are able to achieve a 80% heat transfer at a 50% flow. Now, if you connect it with the system curve, and then you can see that the amount of savings which are possible, because here you are able to achieve a heat transfer at a much lower flow rate, and that ensures that the amount of savings are manifold when you have part load conditions happening, and which is typical. If you look at any load profile, 100% you will be running not more than 5% time. It is most of the time the load is lower than 100%, and that is where you are able to see a huge amount of savings happening. The second control point which I wanted to discuss, and we have briefly discussed when we were looking at the benefits of distributed pumping, and that is the control of the primary chilled water pump. You have already seen that the primary chilled water pump size has been reduced. And now you have 4 temperature sensors across the decoupler. So it's a traditional decoupler. Now what you are seeing a change. When you talk about variable primary, we have always spoken about going for a flow control valve or a bypass valve or a minimum flow bypass valve. But here you are going for a variable primary and a variable secondary side without a flow control bypass valve. And that actually simplifies the system. And what we essentially see is that if you have a flow happening, if the flow on the primary side is higher and the temperature which is going back to the plant room, it is going down, then you need to decrease the primary pump speed. In the opposite direction, when your load is increasing and the requirement of chilled water is building up, what do we see is that the temperature is rising on the building side. And under that condition, you have to increase the primary pump speed. That simple is the control which is possible with the help of a distributed pumping. Now, if we sum up the entire discussion which we have done up till now, what we see is that the reduction of supply line pressure, because here you have a primary pump which is only producing water and taking it up till here. Now, there could be a very valid question that what happens here. So the water moves, it is like a supply header. The pressures are lower in the supply header in the secondary side and higher in the return header. So essentially, these pumps are connected in parallel with individual NRVs to ensure the backflow is not there. And the supply side pressure being lower is essentially what makes the system self-balancing. But we will look at it from a hydraulic gradient diagram, because the visualization is the best way to understand things. So when we will look at the hydraulic gradient diagram, you will really understand where the pressure losses are eliminated in distributed pumping and how do you actually see the savings. We also see that your pumps are connected with the BMS. So if you're having a condition where there is no load, you can switch off the AHU and the pump remotely. And that makes it a system which adapts itself and communicates with the management system. The pump supply needed flow for each branch to match the heat load of the specific branch, which we have discussed. And here you see the primary side automatically balances and ensuring no bypass flow is there at any point of time. Because if there is a bypass flow, the temperatures will vary and the pump will take action accordingly. Now, a valid question which can come is that in a plant or in a building, you need not just have AHUs. What will happen if you have an FCU? So this is the circuit which will actually tell you that in case of an FCU, what we recommend that you need a control for individual AHU FCU in the room itself. So here we recommend, and the FCU sizes are very small to make a pump being put and viable option. So what we do is for an FCU, we put one pump for a set of FCUs. And these FCUs still have the flow control valve, but a single single pump is controlling that FCU circuit. So in a hybrid system, you have AHUs being controlled based on temperature, and FCUs are controlled proportionally based on the pressure sensor or differential pressure sensor. Now, as I have mentioned, that this differential pressure sensor is already inbuilt in the pump. So you need not put any separate sensor. The moment you put the pump and set it across the FCU, you put the set point as the friction loss in that particular circuit, and you are ready to go. So this is how the whole system becomes much simpler, and there is a localized control which makes the commissioning very, very easy. We touch upon some of the projects which we have executed in India. So we have worked across various segments. We have done work on hotel. We have commissioned projects in R&D centers. We have worked on industrial buildings, a retail store. We have given a system for an IT park, and we are working on 2 metro stations. So it is a wide spectrum of type of buildings where we have been able to position the distributed pumping system, and we are seeing the savings happening. Now, if we just look at one of the examples and do a comparison vis-a-vis a variable primary only system, what are the kind of savings which are possible? Now, as you have seen in the system curve diagram, this is nothing but I have translated that system curve and we have put it in the form of a bar chart. And that actually tells you that as the load reduces, you are able to achieve much higher efficiencies. For this particular project, we were able to achieve at 100% load, 22% savings. At 75%, we had 49. At 50%, we have 70 saving possible. But this is a particular project. It may vary from project to project, but it will be in this kind of pattern only. Now, we discussed about the minimum pressure part and how when you have a traditional system which is pressurizing the entire circuit. If you look at this light blue line, this is actually the pressure which is created by a conventional variable primary system. And do you see the orange lines? These are nothing but the actual requirement. So you have to actually run the pump to ensure that we are able to take the water till the farthest point. However, the requirement is much lesser. So what do? We have to throttle and we have to ensure that the flow is balanced in each equipment. And this is the large blue lines which you see is nothing but the killing of pressure. And this visualization can be very well seen if you just put that conventional system on the backdrop and you see on the front what you have in a distributed pumping system. So here you have a pressurized line in the primary side. So this is where the blue line is bringing the water to the decoupler. This line here is the decoupler. And this is where you have the blue line, which is the supply header. And each pump is pulling the water from the supply header and leaving in the return line at a slightly higher pressure. And that is why you have the supply pressures lower than your return pressures. And this actually makes the system much more efficient because here you are not building the pressure and killing it. You are only generating the pressure which is required to overcome the friction loss. If we look at overall profile for a period of 5 years, we are able to see from a baseline pumping to a distributed pumping a saving of around 63% over a period of time. But this is the OPEX part which we have discussed. It is very important for us to look at the CAPEX part also. And the CAPEX part, if you see from a conventional, means a manual balancing kind of system with a flow control device, and you have a PIBCV valve kind of a system. When compared with a distributed pumping system, you actually see that a system with an automatic balancing valve is almost at par in the cost with a distributed pumping system. Whereas you actually see a slight increase of around 20% when compared to a manual balancing system. So this is the kind of a price difference at the CAPEX we are looking at. But look at it now. You see a huge savings in terms of the man hours needed for commissioning. Now, you do not need a complex BMS integration because here, you have an individual pump which has a proper communication channel and giving a localized information to your BMS. So you have much more information which is available, and it is seamless because the moment you know the communication protocol and you connect the system, you have the entire data available. The installation is much easier because the moment you install a pump, you have the entire controls, the sensors, the intelligence, everything inbuilt. So you need not do a complex programming to commission the system. And then in terms of control strategy and balancing, overall, if we see in terms of man hours, you actually see an improvement of around 75% based on our experience in the site commissionings which we have done. The last but not the least is that the design which we are talking about, or our circulators, it is not something which has come up now, but it is a robust design which has developed on a platform over decades, and the pumps are into operation for decades into various circulation applications in both heating and cooling. So it's a very wide and a robust range which has developed and evolved over a period of time, where we have brought in a lot of intelligence and customer feedbacks into the design of the pump. So it's a very robust solution which we have now with the distributed pumping. We have the range of Magna 3, which covers from 70 meter cube per hour flow up to an 18 meter of head, which is maximum. And this covers mostly a mid-sized commercial building is covered with this flow rate. But if your flow rates are bigger, then you can either go for a twin head systems, or you can go for a range of pump, which is our TPE2 and TPE3 range of pumps. You are able to achieve much higher heads to the tune of around 25 meters, 24 to 25 meters as a maximum head, and a flow of around 75 meter cube per hour, which primarily covers most of the commercial buildings. But if your requirement is higher than that, you can consult with Grundfos, and we can work out a solution for this. We have already discussed about the twin head pumps, so I will just move ahead and go to the summing up of the key points which we have discussed today. The first thing, which is very, very important, and I would like to connect here with the initial point of digitalization, which we discussed, the easy commissioning and the host of data which is available for actionable insights. And that is the primary benefit which you get out of distributed pumping. The second is minimum pressure and maximum savings. We have discussed that the sizing of the pumps reduces, the pressure in the entire circuit reduces, which we have seen in the form of a hydraulic gradient diagram. And that essentially translates into savings. So it is nothing that we do something which actually brings a saving. It is just a design change which happens, and you are able to achieve the savings. We have seen that it's a demand-driven solution, and the kind of controls which are there, we have discussed that, and the kind of advantages you are able to achieve with the help of localized controls. You have a host of data available from AHU and FCU level for optimization and actionable insights. You don't need any kind of remote sensors. So that is again one of the pain points which have come up in our discussion with customers, that what happens when you have remote sensors, and the communication cable is much long, and sometimes the sensors are not put. Now, from Grundfos, there are two solutions. One is a distributed pumping, which we have discussed more in detail today. But another is we also have a wireless solution where you can put the sensors with a wireless receiver and transmitter. So with the sensor, you can put a transmitter, and if you have a remote location where the panel is lying, you can put a receiver, and that is how you can avoid this pain point of having remote sensors. But that is another solution which we have, and how do we take care of that pain point is just I wanted to bring to the notice. The second last point is the temperature-based flow control, and it's really amazing that the entire circuit is running on temperature-based control. The entire control of chiller is on temperature. And the moment you have a pressure-based control combined with a temperature-based control, there is a limitation on the amount of savings which are possible. Now, one of the reasons why you have seen that the flow, the system curve in a distributed pumping was not changing is because of this temperature-based control. And that is an essential benefit which you get. The last but not the least, if you have a variable flow in primary and secondary side, and when you have both primary and secondary side control based on temperature, then this variable flow in primary and secondary side is the most optimum way. If you have a system where one side is a pressure-based side and another control of pumps is on temperature, then the kind of optimization possible is limited. So these are the key benefits which we see, and these are the benefits which actually directly connect with the digitalization. And I said in the beginning that digitalization is all about change in the culture, the way we look at our systems in the buildings and not just the equipments. So with this point, I just end my presentation. Over to the ASHRAE Chandigarh chapter, and wish you all a Merry Christmas and a very Happy New Year.
Thank you very much.
Thank you.
Thank you so much, Mr. Gaurav. This was a very enlightening session. If there are any questions, we would like to take it up. Yeah, there are lots of questions. Is distributed pumping the same concept as of the primary flow and the secondary flow?
Sorry, can you just repeat the question?
I will repeat the question once again. Yeah. Where is it? Where is it? Can we optimize an already existing pump performance if it is not right to the requirements at the time of the initial installation?
Initial installation.
Right.
So, my answer to that question, because I would rather need more details, but then if I just go by the information which is available, if you have already reached to a stage where you are installing the pump, then there is a very limited scope for us to make the changes. So we will have, as I said, that we have to start right from the drawing board when we are designing. So uh, when you are already installing the pump, then the only thing which remains is that you have a proper controls which can ensure that it adapts itself to the changing conditions. So with the amount of uh, uh, data which is available, you have to decide on the kind of control mode which you can put in, and based on that control mode, you have to ensure that how you adapt the particular pump. So maybe if you can just come on the speaker and whether I've answered your question or you want some.
Yeah, you can unmute yourself if probably Mr. Amit. If you have any question, you can unmute yourself and you can ask whether your doubt is clear or not. Yeah, another question from Mr. Amit. Only 50% saving in pumping, but how much overall percentage? I think there is some disturbance. Okay. Yeah, probably now it will be audible better way.
Right.
50% saving in pumping, but how much overall percentage savings achieved in HVAC system by distributed pumping?
Yes, so it's a very good question. And as I have discussed in my presentation, is that the savings on the pumping part is very much visible and is quantified based on the calculations which we do. But there are savings which are happening on the chiller side also, which, as I've shown in my slide, it was in the range of 20 to 28%. We are able to achieve, and if you compare the entire savings, then you will be able to achieve plus 25% savings on the overall system if you compare the entire plant energy consumption. So it varies from plant to plant, as I said, because in this particular example which I had taken, there we were able to see an improvement in the delta T across the chillers. So we were able to see a very large savings in the entire plant room. So it depends upon the system and the kind of equipment we have, but we do have savings happening over in the overall system. It depends upon the kind of system which we have. It varies from case to case basis.
Okay. Yeah. I think The doubts are clear. Another question from Mr. Amit itself: is distributed pumping the same concept as of primary flow and the secondary flow?
Okay, very, very good question again. So the answer to your question is there are certain aspects of a primary and secondary flow you can see in the distributed pumping system. Like for example, in a primary secondary system, here you also have the primary pumps which are designed only for the production loop, and you have one set of secondary pumps or maybe a zoning which takes care of the entire circuit. But the controls in case of secondary is also, or the hydronic design in case of secondary also is a pressure based system where you pressurize the entire supply line and then ensure that the flow control is happening with the help of throttling devices. So it is not completely distributed pumping. I would say that a distributed pumping concept takes all the advantages of primary flow and secondary flow, plus it adds many more advantages. So from a primary flow and a secondary flow system, you still have a pressurized supply header, which actually ensures the killing of the pressure which is generated by the secondary pumps. That part is eliminated when you go for a distributed.
Right. Okay. So next question is from Mr. Pramod. Temperature-based control is a nice energy-saving technique in HVAC system. Okay, this was just a viewpoint.
Right. Thank you.
Share this PPT on the mail ID. Okay, so we'll get in touch for that, whether the PPTs are available or not. Otherwise, the entire presentation is always available. You can view the presentation in the digital format in the YouTube channel. Yeah. Okay. By discussing particular models of pumps, it appears to be commercial against ethics and ethos of ASHRAE. No, not really. What is the range of the payback period and comparison of the conventional and the distribution pumping system from life cycle cost point of view? Where is it installed, in India or in UAE?
Yes, so I have shared the payback period calculation, and as you have seen that from a conventional system, if you see uh, the PIBCV based system with an automatic balancing system, and when you compare with a distributed pumping, the capex is almost same, or there's a very slight variation. As I said, it depends upon the project to project. So distributed pumping, as you have seen that each of the AHU pumps are designed for the location, so for their individual loops. So we cannot generalize a payback period. We can do a calculation for your exact requirement, and we have a design team which sits in India, who can work based on your particular project. And we will be very happy if you have any project in mind. We can do a life cycle cost analysis and give it to you. But that is something which happens on project to project basis, and you can share more details, and we can come back to you.
Okay, great. If one goes for IE5 motor for with temperature-based flow control, what is the possible overall pump efficiency near the BEP as per the system curve?
Okay, so if you go for the pump with an i5 motor, then the efficiency change which will happen is in the overall IKW for that particular pump. The i5 motor will not have any impact on the pump efficiency. But if your question is that for these particular pumps, what are the efficiency values which are possible? Then these are small flow rate pumps, and in these pumps, you are able to achieve an efficiency ranging from 65 to 75%. If you go with TPE3, you will have a slightly higher efficiency also possible. But the important point is about the energy efficiency index. So when we talk about circulator pumps, it is not the efficiency, and why when we talk about IE5 motors, the efficiency comparison is done based on energy efficiency index, EEI. The energy efficiency index is basically how closely you are able to control the pump as close as possible to the system curve. And the amount of error is what you actually quantify here. Now, as per the European Union, the pumps or circulators having lesser than 0.2 energy efficiency index are acceptable and are good circulators. Grundfos is able to achieve 0.17 as an energy efficiency index. And that is where you are able to see the pumps, how closely they adapt to the system curve changes. So, and with respect to the other details for the pump performance, we can share the data, and we can share the details of the pumps in terms of how the energy efficiency is changing over different load conditions.
Okay. I hope the doubt is clear. Now, the next question is it necessary to have individual pump for each AHU in the plant room, or it can be proposed for group of AHUs in the plant room?
So a very good question. If you go for a group of AHUs for a plant room, then it essentially becomes a pressure-based control, because here the AHUs which you are clubbing, as you have seen the way we club the FCUs, you have to get the temperature signal of the return air or the supply air, and there has to be some device which should modulate based on the temperature control for that particular AHU. So if you have a set of AHUs connected, then it becomes a zone-based system where the control is on differential pressure instead of temperature.
Okay.
It will not be essentially a distributed pumping, it will be a zone pumping.
Okay. Right. So, what is the maximum flow pump available?
Yes, so I have said the Magna 3, the maximum flow available is 70 meter cube per hour. And you have TPE3 where the flow is up to 75 meter cube per hour, but you are able to achieve higher heads when you go for a TPE3 design. So if your heads, maximum heads in case of TPE3 goes up to TPE2 and TPE3, the TPE range you can go up to 24 to 25 meters. So
okay, there's a point mentioned by Mr. Pramod. Head cannot be more than 18 meters in Magna.
yes, that's right. When you go for Magna pumps, but if you have a system where the heads are higher requirement, then we will do a design separately, and we have to look at that system separately. But normally what we have seen, when you have the flow restricting devices removed from the entire circuit, and when you are designing the pumps for their individual loops, the heads optimize much more than when you have a conventional system where you have to have a flow restricting device. So when we work on a particular project, there's a large amount of reduction in the differential pressure. But if your project is such where even after doing our designing, if we are getting higher heads, then we will have to look for some other pumps. But that is done on a project-to-project basis, where we can look at higher pumps, flow rates, and higher heads also.
Okay. Niladri ji, I think he has a question. I'll just unmute. Okay, you can unmute yourself. Let's have your question, Mr. Mushkil. Yeah, let's go ahead.
Yes, 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 yes. You are audible.
Normally in design, what we do for variable pumping system, variable flow water system, we
Yes.
use
Are you able to hear the question? Niladri ji, can you be a bit, you're not audible properly.
Yeah, now it's okay.
Thoda sa, if you can come close to the mic.
See, in pump, we use pump controller which are connected to the differential pressure systems and also to the all the temperature sensor. Wherever the sensors they are there, and actually these pump sensor can give signals to the pump. Now here you are telling that this is the temperature which controls the flow rate. Now how you differentiate these two? Because all our design is use pump controller and transducer and with pressure differential transducer and temperature sensor. These are all connected to the pump controller.
Right, sir. So, absolutely right, sir. And the difference which happens is that when you have a conventional system where you are pressurizing a supply header, we have to have a flow restricting device. So in that particular case, the temperature signal has to go to a turbo or a PIBCV valve to control the flow, because you have a system which is pressurizing the line, and now when you have to see how the load is changing, you have a valve which ensures that opening and closing is done when the load changes. So if the load is increasing,
Temperature sensor directly goes to this type of pump. What you are saying?
no, sir. In that case, the temperature signal goes to the valve controller. Yes.
It will go to the pump controller.
No, sir. If you have a temperature sensor in a conventional system, signal goes to the PIBCV valve or a flow control valve, and the pressure, the differential pressure sensor, that signal will come to the pump controller.
So this will go directly to the temperature or transducer, what they are, temperature.
Yes.
Actuator, this will go directly to the
pump now.
Okay. But this product has been launched, this one?
Yes, sir. Already there, sir.
But now you are using this, the pump bearing is the magnetic bearing.
Sorry?
That motor bearing is a
permanent magnet motor, sir. So,
but you see, we find a lot of difficulty because few area which I work for a chiller actually, magnetic chiller. But it is difficult for repairing and other. These are all complaints coming from the contractor recommending this type of magnetic pump, magnetic system, and permanent magnetic.
So, sir, there is a difference between when we talk about the technology in chiller, that is a magnetic levitating chillers.
Yeah.
Maglev. So it is different from maglev chiller. So it is basically a permanent magnet motor, which is different from maglev chillers.
Using the conventional all the bearing you are using there.
Yes. We have the entire instead of having a coiled arrangement to generate the magnetic field, you have a permanent magnet which generates a magnet.
Yeah. Okay.
Right, sir. Thank you, sir. Hello.
I'm saying that detailed discussion can be taken up post the session. You can just mail your mail ID and phone number so that the questions can come up. And for now, we should close the session. And one more question is left over here. I think Mr. Niladri has sent a question. So you can mail the question and you can get in touch with Mr. Gaurav offline so that whatever doubts you have can be cleared out. For now, we would like to close the session. I hope that's fine with all. Yeah, is it okay, Mr. Gaurav?
Yes, yes, yes.
Yeah.
Yeah, you can send me the questions and probably we can send a reply to all the participants. And in
Yeah,
case
sure.
there's any other question coming up, we will be happy to answer that.
Yeah, exactly. There are many questions coming up, and it would be nice if you can just share your mail ID over here. Or you can just tell me, I'll just
Okay.
type it.
It is Gaurav, Gaurav,
Mm-hmm.
@
@
Grundfos, GRUND
Grundfos.com.
.com.
So all the questions can be sent either to either on the ASHRAE website or to Mr. Gaurav directly, and all your queries will be sorted out. So for now, thank you very much, Mr. Gaurav, for this session. We would like to thank you, and a very happy New Year to all of you, and a Merry Christmas. Let's close the session for now.
Thank you. Thank you, ASHRAE Chandigarh.
Thank you
Thank you very much.
Thank you so much. And it's been a pleasure from my end to be part of the session, hosting the session.
Thank you. Thank you.